So just to tell you a little bit about her, Karen Yuen is the NASA Orbiting Carbon Observatory 2 Science Data Applications Lead and Project Communications Manager. Wow, that's so awesome. Yes, that's amazing. As well as the NASA Applied Sciences Program Performance Lead. Her project OCO-2 is NASA's first dedicated satellite for measuring carbon dioxide from space. It's just blowing my mind while I'm like reading your bio. Her current work is in data user development for applying remote sensing data for science applications, specifically for the solar-induced fluorescence products from OCO2. She began her career at the Jet Propulsion Laboratory in 2001 and has received 8 NASA Group Achievement Awards for her work on various missions. Yuen received her bachelor's degree with a major in chemistry, physics, and French from St. Mary's College, Notre Dame. She pursued an MA in scientific journalism at New York University while working as an editorial assistant for the Journal of Neuroscience. She continued her graduate studies in organic chemistry at Université, whatever, de Paris, je suis something in French, which is amazing. So hot damn, Karen is amazing. I'm gonna hand this over to you and let her show us space from here. So thank you, Karen.
Good morning, everyone. Thank you for having me be here. I think there's a fair number of people who actually stayed for the earlier, that were here for the earlier part of the panel. So I don't mean to bore you. I am going to present a lot of facts. I feel very strongly about presenting facts because that's what I feel people need. This is what's going on. This is what we see. And as time goes on, I have two feelings. I updated a few of my charts. And the tough part about this is as time goes on, I see certain trends. And trends are very important to scientists. And what the trend's showing me basically reaffirms what I thought was happening. So it's always good to know that as we continue to make our measurements, these trends, we've been right all along, because as human beings, we like to be right. We like to feel like we're doing something right. But then the second part of feeling is just a sense of a great sadness because what the trend indicates to me is, we have some problems that are ongoing. And what you're doing here, for those of you who are attending and having to make the choices that you do, I applaud you, because every little bit helps our world, and we all have our different ways of helping folks, and I think it's important that you're making the decisions that you do. And so, yes, everything I'm going to talk about is my perspective from space, and I'm going to present some facts, and I know we're short on time, so I'm going to just blaze through some of my charts and open myself to you guys for questions. So, by the way, this is it's an artist rendition, but it is actual data of what we see from space. Because the actual data isn't very pretty, so we needed somebody to put this in perspective for us. This is through the LA Basin, and what you see, the little parallelograms across the areas, that's actually what we can measure from space of a given time of the concentration of CO2 all across the basin. And those of you, if you follow the news a little bit, last week we actually had a really, really big event. We had 5 of our papers accepted to the Science Journal. It's a huge honor. And they covered all the different areas that we have studied and the data sets that we have. If you get a chance, please take a look at it. It's the latest edition of Science, and it's pretty mind-blowing if you see what's being done. And of course, I mean, full disclosure, I'm one of the authors on one of the papers, so I'm going to be So let's see. All right, this is just a snapshot. How many of you knew that NASA did Earth science? Oh, well, okay. Most people don't raise their hands. Well, thank you for knowing that, because we always feel like, oh, nobody knows that NASA's doing Earth science. So we have this tremendous fleet that's flying right now. When I started my work, a lot of our concern was the time frame that we launched these satellites. We used to put them up every few years. It's to replace satellites when they get old. We haven't been putting up them up as quickly, and they start dying off, and they do very important science. So also as of a week and a half ago, unfortunately, we lost another satellite, which was the GRACE satellite. For those of you who have been following along on how we monitored drought in California, when they make that big impact, when they say, oh, we're in drought, it's because GRACE has been studying the aquifers. And unfortunately, GRACE has been flying for 15 and a half years. And the batteries and other situations, it's not functioning anymore. So we actually lost a satellite a week and a half ago, and the follow-on isn't going up yet. So that's an unfortunate loss for the science community. And, but OCO2 is up there, and as you know, OCO2 is NASA's first mission dedicated to studying CO2 from space. Why? CO2 is probably the most important greenhouse gas. It's not the largest greenhouse gas. Water vapor is, actually. But why do we care about CO2? Us. We have the biggest influence of CO2 because we emit CO2 and we absorb CO2. So that's why when they talk about anthropogenic causes, we are a factor. That's why we look at that. And I have a little video for you because I love cartoons. So I worked with someone to make a cartoon that should help give you an idea of what the mission is about.
When it comes to carbon dioxide in the atmosphere, we've all heard a lot about where it comes from. But what happens to it once it gets there? Lots of things, actually. The atmosphere, oceans, forests, and soil are all constantly trading carbon dioxide with each other in a global exchange called the carbon cycle. Some parts of this cycle are sources of carbon, while others are sinks. All of these natural sources and sinks are pretty well balanced. Just as much CO2 comes out of the atmosphere as goes in. But now we've got a problem. Ever since the Industrial Revolution, we've been tipping the balance, adding a CO2 source without providing a sink to match. Some of this extra CO2 is being taken up by natural carbon sinks, but not all of it. And on top of that, the efficiency and availability of these sinks may change over time as they react to changing climate conditions and as we clear forests for agriculture or homes. If we want to know what's really going on with the carbon cycle and how it may affect climate, we need more information. After all, we can only manage what we can measure. That's where the OCO2 mission, the Orbiting Carbon Observatory, comes in, NASA's first satellite designed specifically to measure the global distribution of atmospheric CO2 from space. How will it do that? By measuring the sunlight that bounces off the Earth's surface. On its way through the atmosphere, this sunlight interacts with CO2 molecules in the air. CO2, like other gases, absorbs only certain colors of light. OCO2 is tuned to look at these specific colors, and by measuring the amount of light that's missing in each one, we can figure out how many CO2 molecules got in the way. As OCO2 orbits the Earth each day, it will make hundreds of thousands of CO2 measurements. This high measurement density will give us far more information about where and how CO2 is traded between sources and sinks. Plus, measurements collected over weeks and months will capture the variations due to seasonal changes, allowing us to watch the planet breathe. If we can understand better where these carbon sinks are and how they store carbon dioxide, we'll know a lot more about the processes that control the rise of CO2 in the atmosphere and what role it might play in our changing climate. So take a deep breath and get ready for OCO2.
When we talk about CO2 and the measurements, and people talk about, oh, what's more accurate and how do we do things, we have a lot of accuracy and precisions for ground-based measurements. Unfortunately, think about how many ground-based measurement we will need on the ground to cover everywhere. We can't. In the past, what we've done is that we would put them next to certain plants or buildings and whatnot. It's just impossible to have one everywhere. So the observation from space was essential for us to really get the global coverage and cover areas where we may have, or we can't get to, for example, over the oceans. If you look at this image here, the yellow dot represents clusters of area where we were able to get CO2 measurements from the ground. Those were where the base of the grounds are. The red lines would be how OCO2 covers the planet. Now, we make our measurements we can't see through clouds, so we say that we make a global measurement, meaning that we get the global coverage every 16 days, because what we have to do is basically calculate around the clouds. So what we can't see, we throw that data out, and then we just keep looking at, so we have one snapshot of the globe. But it would be the first time that we're able to see it with the sort of precision that we need, and that precision is we have to be as good as less than 2 parts per million difference relative to a ground-based measurement. At this point right now, we're at 0.5 parts per million, so we're doing very well. And so that gives you an idea why we needed this. So for years and years and years, we've been talking about measurements before remote sensing, before a satellite. You can see what we were able to see before, and now what we can see with the satellite. And but I'm going to go, does this look familiar to folks? Okay, this is the Keeling Curve. Charles Keeling, back during the International Geophysical Year, proposed to measure CO2 from Mauna Loa, and he started this iconic measurement. And he's been doing it for a very long time, and it's one specific point. It hasn't been moved, and they've been making this measurement for over 50 years, and what we have seen is growth. And if you look at where he started out, and if you look at where we are right now, that's one point, one measurement. And when I started working on CO2 back in 2001, when we wrote the proposal, the fear was we wanted to launch this particular satellite before we ever reach 400 parts per million. That was a concern. And to be honest with you, when I started working on the proposal, the idea of us reaching 400 parts per million just seemed like something that was, it was, in a sense, an arbitrary milestone because it's a round number, but it seemed so far-fetched that we would ever reach 400 parts per million. And unfortunately, now mind you, it took us all of our human history lifetime to reach 400 parts per million. I've been keeping track whenever I do this talk, and I just update the trends. If you can see, September of 2016, it was at 401. September of 2017, we were at 403. And if you will look at what it was 10 years ago, and you look at what it is now, it's the up-to-date weekly average that we have. Not only are we gaining CO2 in the air, it's also happening faster and faster. And that's something that the models have predicted, that it was just going to accelerate. And we are seeing that. And I actually have proof of something that's a little troubling for us, because one of the ways that we share our data is through colored maps. You probably see that online in images and whatnot. We'll show a color map, and usually we have red being the high end because it's warm, and people say, oh, it's a higher number. And you have a range that you show that will say, oh, it's 380 to 400. So if you think about it, if we did this 10 years ago, if you consider 380 as a high, we would maybe have it at 350 to 400, and we show the range, something like that. Once you pass that, you have to keep moving the range. And in the last year, we had moved it to 410, and then we had to adjust it again and move it to 415, just to allow that it wouldn't oversaturate when we use the colors to do the maps, because it's just moved so much. And that's just in the last year, just so we can show our data in a visual way. Because we actually ran into this problem with another tool that we were using, where we actually set the upper limit at 400. And when we put our data in to show this on a global scale, the entire globe was red. And we're like, oh my God, what the heck happened? And we couldn't understand. We were thinking, oh, we must have messed up with the data, we messed up with this, messed up with that. Looked at everything until we looked at the scale, and we were like, oh, it's at 400. Well, we're consistently right now over 400. That's why the whole globe is perpetually red. We actually had to completely shift the scale to accurately show any variation. That's how much things have changed. So I want to show a very short video, which I love, that was done, and it talks about trend and variation, and I think it's very important to show this.
You're looking at the dog when you should be concentrating on the owner. As you can see, the dog is all over the place, leaping and bouncing, sometimes upwards, sometimes downwards. But where do you think it'll be in 10 seconds' time? Around here, right? But at this moment, the dog is on its way downwards. So why do you think it'll find itself up there? It's because you've noticed the owner. The owner is the trend, and it's he who determines where they both will be in a while, as a bit longer than a couple of dog bounds. He could change direction. There's a lot we don't know about this guy, but everything we do know indicates he's heading in that direction. The owner is the long-term trend. The dog is the variation around this trend. Or, the owner is the climate, the dog is the weather.
Teddy?
I like showing this one because I often get questions when asked when people are like, oh, well, we had a really bad snowstorm last year, so where's global warming? I was just like, oh my God. I'm like, oh, there can't be global warming because it was so cold last winter. Or, oh, that can't be global warming because it's like, okay, global warming it's a terrible expression. It doesn't mean just warming. Yes, the planet itself is warming, but there are consequences, and our ecosystem varies depending on its response to that. And so if you ever get in a situation and people say, oh, it was really cold last year, so how could there be global warming? You should show them this video and say there's weather, which is short-term. It can be all over the place, but the trend, and we have long-term trend that shows we're going a certain direction. So these are some of I said that I would present facts. I don't mean to depress anybody, but this is the truth. These are the facts. All of this, all the sourcing is on the bottom left. If you guys take this, you can look this up yourself. You can follow it. This is where we are. As you can see, it's pretty much a straight line trend that's been growing for a very long time. You notice that this one is 2006. It doesn't go all the way back to 1958 when Dr. Keeling started making his measurement. It's been going up. But if you look at the other one that's at the bottom right-hand corner, that shows the variation. It includes some of the ice core samples and measurements that we have, so it goes back obviously a lot further. And what you will see is that there has been tremendous variation over the years, a lot. But what's startling is if you look at, as we pointed out, 1950 and on, where the variation is, and the variation is basically, it's just gone straight up. That, in the time scale, if you put it in that perspective, since human beings have been there, and our effects, if there's any doubt, you should start looking at some of these graphs. Even if you put, this is an extreme example, and I'm not advocating for this, when people sit there and say, oh, so what, if the gases are going up, nothing's gonna happen to you. Even a smallest child knows, if you put them in a room and you pump gas in there and it stays closed, because that's what our planet is, that's what our atmosphere does, is it protects us and keeps all the gases and everything in. If you keep increasing the amount, do you really think nothing's gonna happen? That's like sticking a tube from your car exhaust and putting it back inside your car and say, yeah, nothing's gonna happen to me. There's no effect whatsoever. Think. So that's the carbon dioxide trend. What other trends do we have? So we actually, let's see, this one is the sea level rise. Living in California, we're very well aware of the erosion of the beaches and sea level rise. There's another state on the other side of the country. They should be very concerned. They are, because after the hurricanes, they saw some of the devastation from that. That's been going up. But I would like to point out the number of the rate of change, 3.2. That was happening 2 years ago, and it's 3.4 right now. Why are those numbers significant? When I first started at JPL, the magic number that I was quoting, the rate of change at that point was 2.7. So once again, sea level rise is accelerating. That's another measurement that in my lifetime, I'm watching things happen in a trend, but it's also happening faster and faster. And the bottom numbers show the correlation between the temperature rise over time. I did a circle around y-axis for you to show the acceleration, because if you look to the one from the left, we're looking at scales in quarters, 0.25 to a 5. Now, to account for how fast things are changing, we actually are going by halves now, just to accommodate how we would show the numbers for the change. And what else is happening? So there's sea level rise, CO2 is going up. Let's see. Oh yeah, melting. Both poles. Greenland, which is a sea ice, that's been going down. That rate of change is happening faster. Antarctica. I can't say conclusively what's going on because we don't know. For the first time, ironically, Antarctica, we knew that it was thinning at the edges. It was getting thicker in the middle, but there's a giant crack in it right now. I don't know if you guys knew that. That happened a couple weeks ago where I was reading an article. They actually found there's a crack in the ice in the center of Antarctica. But we don't know why it's like that. So there's researchers that's going to look into that. But that's a little alarming. And so all this is to show when people are talking about climate change and our concerns for it, most what people do not realize is how long we've actually been studying it. So I have another brief video to show you.
It's 2015, and climate change is one of the biggest challenges of our time. But while it may seem like all of this fuss over global warming is a recent phenomenon, concern over the role of atmospheric carbon dioxide in our planet's climate has a long history. Let's step back in time for a minute. With the transition to new manufacturing techniques and the rapid exploitation of natural resources, the Industrial Revolution of the 19th century marked a turning point in how we as humans relate to our environment, prompting concerns about how we might be affecting our surroundings. In 1824, Joseph Fourier was the first to suggest that without our atmosphere, the Earth would be a very frigid place, and the term greenhouse effect goes all the way back to this early paper. A few decades later, John Tyndall isolated certain gases, including the potent greenhouse gases carbon dioxide and methane, that are especially good at absorbing outgoing radiation. And by the end of the century, Svante Arrhenius was calculating potential effects that human emissions could have on global temperatures. In the 1930s, E.O. Hulbert found that doubling atmospheric CO2 could cause the Earth to warm by 4 degrees Celsius. And a few years after that, Guy Callender identified a rising trend in both global temperature and CO2 concentration over the previous few decades. The mid-20th century was a time of great change for government involvement in scientific research. In 1957 to 58, the International Geophysical Year brought 67 nations together to participate in collaborative projects tackling outstanding problems in the earth sciences. As part of these efforts, Charles Keeling began direct measurements of atmospheric CO2 in 1958 and soon demonstrated a steady increase each year. Public health concerns like London's Great Smog of 1952 and the hole in the ozone layer inspired investigations into the links between human activities and climate feedbacks. At the same time, geological research into deep-sea sediment cores and Antarctic ice records started to fill in the bigger picture of Earth's climate record over billions of years. In this context, the unprecedented warming trend, noticed a few decades earlier and confirmed by new studies, was pretty alarming, and the Intergovernmental Panel on Climate Change, or IPCC, was established in 1988 to gather and interpret cutting-edge research. That was a quarter of a century ago, and since that time, the IPCC has put out 5 major reports confirming that the planet is warming, that human activities have and will continue to contribute to it, and that we're already seeing its effects in global mean temperature rise and extreme weather patterns. In 2013, atmospheric CO2 reached 400 parts per million for the first time in history. And last year, this trend continued, and 2014 has been confirmed as the hottest year on record. We are already feeling the effects of climate change, and we cannot ignore or deny the consequences of what is going on. We need to better understand how the Earth system works and responds to changes, especially the carbon cycle, and that's why NASA launched the Orbiting Carbon Observatory 2 last year. If If we can track down and measure the CO2 being absorbed at carbon sinks and emitted at sources, we'll have a better global picture of where we're headed. OCO2 is part of a long tradition of engagement with the natural world, gathering information, staying curious, and preparing for the future.
So going back to OCO2 for a second, I wanted to what I was telling you before. This is just a picture to show you. This is an example of how we sample our maps, and I wanted to show you. This was through 2016. We were actually looking at our data, and our scale was 405 parts per million. When we had to update this recently for our science paper, to extend it for March 2017, we actually had to move our scale, the red scale, from 405 to 415 parts per million to accommodate how we would show the variation. We actually had to limit ourselves because we wanted to be able to show more variation. If we could, we would actually accommodate for it more, but we didn't want to alarm anything. And this is just within the last year with our data, what we can do. It's upsetting to me that I have to share this information because as proud as I am of our work, it's hard to watch something happen and say, okay, no one's listening to us. And it's just like my colleagues who worked on GRACE, who told the state of California for 10 years, you're in a drought, you're in a drought, you're in a drought. Nobody listened until it's like, oh crap, we're in a drought. Really, I've been telling you. So I like doing these talks to let folks know it's happening. And this is my little cartoon. I'm going to go through and say, so you know that all this is happening. We have all of this data, global data. It's not just like, oh, this is what's happening in the United States. This is happening in the Southern Hemisphere. This is happening elsewhere. What does this all mean? Well, the planet's not doing so well. But I say this, and I'm saying this to all of you, I have a personal beef when people sit there and say, oh, we need to save the planet. Trust me, the planet's going to be fine. It'll recover. We won't. This is my personal opinion, but as a species, mammals are very, very fragile. We don't like it when it's too cold. We don't like it when it's too hot. We don't do well when there's no water. We don't do well when there's no food. Okay? When we change how we are used to living and how we grow things and what's available to us, we're very vulnerable to it. I'm just saying, I'm presenting the facts to you to think about this. Because most people sit there and say, oh, we need to save the planet. So I'm like, no, save yourself. So, and what does this all mean? With everything that we do, with the application development that we do, these are the images. With all the devastations that we have seen recently, I'm just going to point to California for a moment. We knew there was going to be bad fires. We knew. It made sense. Why? We had a really big El Nino in 2015, 2016. We had a really bad. What does that mean? Northern California got a whole bunch of rain. I cannot believe how many people in Southern California say, oh, El Nino, didn't really happen. We didn't get that much rain. It's not just about you. They got a whole bunch of rain up there. I mean, it replenished their aquifers. It was amazing. But then we're like, ooh, all that vegetation. That's what all the fire scientists were saying. Oh, crap, all that vegetation. We knew it was coming. And then you have all the hurricanes with all the water's been really warm. Why are the hurricanes so intense? Because they need the fuel, and they draw that fuel from the heat in the water. If people sit there and say, ooh, it's nice, the water's warm, and we're all like, that's not a good sign. It's literally the engine. It feeds it, you know. I'm not a hurricane scientist, but I was a little bit perplexed last week when they said, oh, there's a hurricane off the coast of Ireland. I was like, Ireland? I'm like, Atlantic's cold. How did it get so warm that it the water's warm enough to feed a hurricane in Ireland? I don't know, but correct me if somebody else knows. I mean, is this, you know, I was a little bit surprised that it was on the other side of the Atlantic. I'm used to it going to our side. So that was alarming. And so I keep these pictures up for you to show that it's really about us. It's about food availability to us. It's about our living conditions. But also, if we look at the global sense and global picture, there are a lot of people that are moving because they need food. They have to move away from coastlines because of the erosion. And when you have a lot of people moving very quickly elsewhere, like millions of people, even thousands of people, look what's going on in the Middle East. Look how we're dealing with things. Everybody's saying, oh, no, you can't be here. That's just going to get worse. Where are we all going to go? Oh, by the way, this planet, just so you know, we can't live in the ocean or on the water, so that's over 70% of the surface area. That leaves 30% of the land area. About 15% of it we can't live on it, because it includes Antarctica, the deserts, and the mountains. We can't get there. So that's about 15% of the surface area for everybody else to move to. Not a lot of space for us to move around. Facts. And if I could just end with something, for those of you who are interested in this talk and you want to have it, one of the things I really want to do is to let people know that there's a lot of fake information out there. So I ask, I'm calling it fake information. You can call it whatever you want. We have certain words that we use in the science community that gets misconstrued outside, and these are just some of the common terms. I always joke around with my colleagues that when we talk about our models, because we always use our models, and models are a great thing. You wouldn't be able to turn on your 6 o'clock news and be able to prepare to dress for today or tomorrow if we didn't have model data. That's how we do the forecast. That's what it's based on. But I tell them, I said, we go out right now, even in La Cañada, and we randomly pull 10 people and say, name a model. Trust me, they're not naming one of our models. They're naming a Victoria's Secret model or something like that. I mean, that's just like, it's a joke, but it's just the disconnect sometimes we have. And so I will leave a little bit of time for questions, and for those who are interested in this, would they get it from Linda or somebody, whoever needs it? Okay, you can share that, okay, great. So I am gonna conclude there and ask if there are any questions.
So we're lucky to have people like you that are kind of behind the scenes, but not really doing this work. But I wanted to ask, what do you think are solutions, timely solutions? Because veganism, I think, is one, but I don't think it's timely. Not enough people. It's not gonna. Now nobody's gonna turn vegan overnight. I don't think the carbon tax is a good solution. I think it's like a Band-Aid. So I just wanted to ask you, like, is like the implementation of like regenerative technology a solution? Is that possible, or what is your take on that?
I firmly believe in the power of what people can do to change things. They just have to want to do it. The alternative energies, that's not even, it's a term that they say, it's alternative. Everything we're using right now is a finite resource. We have to find other ways. There's no way about it. And maybe it'll be okay in our lifetimes, but I have a daughter. I would like to hope that I'm leaving a better world for her and giving her possibility to do the good work that she wants to do and be able to live the life that she can and continue on. I mean, that's what it's about. It's not just about our happiness and our comfort. It's got to be something more. So I think that there isn't just one solution. There are multiple solutions. It's always good to see people who are willing to do more. And I think that it's important just to keep marching forward. Whatever we can. Not everyone can do everything, but if you can do one or two things, but you stick with it, I think that will go a long way. So if you choose to be a vegan, and that's a life, and you share that with folks, and you can influence folks to live a certain way, then I think you're helping out.
Thank you.
Okay.
I just had a question, and how I was wondering what's a better way that we can approach this topic and get the seriousness of this issue across to people who are still very skeptical about it. Mm-hmm. Of course, we have facts, as you presented, but what's a better way to promote that seriousness?
Knowledge is power. I cannot say this enough. Here we are at UCLA with the students, and what they're learning, knowledge is absolute, it's power. The more you know and the more you understand, the more you can share with folks. I firmly believe in that. It's just like you educating yourself, and being able to talk to more people. There's strength in numbers when there are more people that do that. I really, really, because if you hear somebody that's like, oh no, this isn't happening, and you have the facts, you can go to them and say, no, that's not exactly true because.
Hi, so my question was about the contribution of methane gas to global warming, and I was
Yes.
wondering if NASA is also looking at methane concentrations in the atmosphere. In addition to carbon
Absolutely.
dioxide.
We're heading to a science team meeting next week where GeoCarb is going to be looking at additional greenhouse gases, including methane. But we do have our instruments flown on airplanes. One of my colleagues actually, Riley Duran, he's the principal investigator for a project where we were out in, of course the name escapes me right now, the big gas, thank you. He was actually making the measurements at Porter Ranch and following up afterwards and seeing where things are, and we're trying to work on how we can improve how the measurements are made and the assessments, and there's a lot of interest in the state of California for methane, so we're working on that. It's just, I'll be honest with you, they don't like to keep us in the budget for this current administration, so that's something that we're fighting for. But we continue to do the good work. But yeah, there's definitely people who want to do the work, they're doing the work, but we do what we can. So, but thank you.